Let's begin our discussion of telescopes by starting with the refracting telescope. And these will work out the principles of lenses bending, refracting light to a focus. So we'll have an objective lens that fits into the aperture of your refracting telescope. The bigger the aperture, the more light collecting power, the more light you can pull in. And the focal length of your entire telescope will be the distance between the objective lens and where you see the image. So if you were to increase the focal length, right, get a longer telescope, well, that's going to help you better resolve objects. Let's go back to picture A, where we have light from star 2 that's in this orangish color and light from star 1 that's in this blue. And you'll bring in your light, and here is the separation between star 1 and star 2. You'll be able to tell that they're distinct, but the image will be blurry. It'll be hard to resolve them. Well, now you go for a bigger, a longer telescope, and that's going to increase your resolution. Now you'll have those two stars further apart in your image, and it'll be easier to distinguish them, to pull out more information. Now, while refracting telescopes are probably the easiest to design and think of, all you need is a lens and an eyepiece, you're good to go, they're going to be problematic. For starters, you're going to need a long telescope. Right? You need longer to do better. And there is a limit. Recall from a previous video that it will have this chromatic aberration happening. When you send light through a lens, the colors will bend ever so slightly differently. So you either need corrective optics or just accept the fact that your color resolution will be distorted by this aberration here. Now, talking about the lengths of these telescopes, let's look at one of the biggest ones, the world's largest refracting telescope, which has a 40-inch aperture size. Right? So down here, that's about 40 inches. For our perspective, here's a scientist and astronomer standing next to the telescope. This one was built in 1893. Now, in order to use this refracting telescope, look at this entire focal length, the floor itself. Here's the handrails in the picture on the left. Here are the handrails in the picture on the right. You actually have this crank system that will adjust the floor, lowering it down so that you can get your telescope at the angles you want to use. Switching to reflecting telescopes, what are the two main properties here? All of our reflecting telescopes will basically compose of a primary mirror and a secondary mirror that will collect the light. In this Newton-style reflector, the light will come in, and the curvature of the mirror will reflect the light back towards the secondary mirror that will focus it into our eyepiece, and you come in a Newton reflector on the side here. Now, a related type of style of reflecting telescope is called a Cassegrain reflector. Same principle here. The light comes in, hits this primary mirror. This one has a parabolic shape, but that will focus the light into a secondary mirror. That secondary mirror bounces it into an eyepiece, and you, the observer, come here to see the image. So, wonderful advantages of this is that the focal length, the equivalent focal length of these reflecting telescopes is based on the path the light takes, how far the light travels inside this tube here. So we're able to create effectively longer focal lengths by increasing the optical path, how far that light has to travel. I want to discuss a little bit more about the geometry of the mirrors we're looking with. We played with lenses in a previous video, so let's talk about the shapes in different mirrors. And here I'll present a nice flat mirror, and this is what most of us will have experience with. You go to the bathroom, look at your mirror here in the morning, see how you're feeling, right? And look at this geometry. It's a nice flat surface. All the rays come in, reflect off in a nice, simple, easy to translate manner. But if I was to flex the mirror, bend it, I would change the optical properties. So let's go big. I'll bring a convex mirror. This mirror vexes outward. Right? And I'll aim this at the camera where I've mounted a blue arrow. Right? You might be able to see the blue arrow. I'll zoom in a little bit so it really comes out. Say hi to the camera, say hello basically to yourselves. And the arrow comes into focus. Right? Now, no matter where I put the mirror, everything looks upright. Everything looks in the correct orientation. You'll be familiar with mirrors like this when you say go to a convenience store. You'll see them, there'll be mounted domes. There'll be domes mounted in the ceilings. And you'll always see everything around that mirror. Right? This is what we call a virtual image. Let's try a different type of mirror. Right? This will be a concave mirror. The mirror caves inward. This one's going to get weird. So let's try and find. Gotta find the arrow. There it is. So at this distance, you see a upside down arrow. The arrow is pointing down. Now let me bring the mirror closer to the camera. Let's come in. No tricks here, but that arrow has suddenly started pointing up. Let's zoom out again. Find it. There's the arrow upside down. So, the distance between the mirror and the observer will change what type of image you see. We'll try to do this again for fun, all right? Upside down at this distance. Let's come in. Right side up. If you were to look at this mirror in person, you'd actually see a magnified version of yourself. So, there's some fun playing with mirror curvatures and seeing what kind of resulting images you'll get out of that. Our reflecting telescopes are going to have a lot of advantages over the refractors. For starters, there is no chromatic aberration. If you have a perfectly smooth, flat surface, there will be no color dispersion here. So you don't have to worry about trying to use adaptive optics to fix the colors that are being split apart. Also, you can get bigger telescopes, bigger in the optical sense, right? You don't need to create massive lenses. You can just toy with the way the light is bouncing around to increase the focal lengths, right? Add a few mirrors here inside your telescope so you can get a larger magnification, a bigger resolution, and a smaller physical space because you're just changing the path of the lights. So, I'll end this by talking about how the largest telescopes in the world on Earth are reflecting telescopes. Here is Keck, one of the biggest out there. This is a 10-meter reflector, 10 meters in diameter. So our reflecting telescopes have a lot of powerful advantages over our refracting ones. The refractors uses lenses, reflecting mirrors. Another thing to take into consideration with our Earth-based telescopes will be the atmosphere interfering with the light coming in. When light comes in, you can think of these nice plane waves. These would be the front of the wave crests coming down. Well, that light's going to hit Earth's atmosphere. There'll be some reflections, there'll be some random variations just to thermal fluctuations. And so it hits the atmosphere and basically a ripple starts to form. And as it keeps propagating down, you can think of it as the signal, the original light source, is getting noisy and noisier. And by the time it's passed through all the different layers of Earth's atmosphere, finally, the light that's traveled across the vacuums of space has reached our telescope, but been severely distorted. So this is a problem that all Earth-based telescopes will have. Now, you put something in space, it won't have that problem. There's less atmosphere way out there. So to see this in action, the picture on the left here would be an image taken on a ground-based telescope, but we're clever, we're smart people. We can start constructing adaptive optics to correct this image here. And so this fuzzy, blurry image, we will account for is trying to account for the height, the atmospheric height between the vacuum of space and where the telescope on Earth is. And when you apply that, you can really clean up the image, create a better resolution.